I'm really honored and pleased to introduce Juan Diego Medrano, who is a postdoctoral fellow in the Super Lab of ETH Zürich, a partner of the Photo2Fuel consortium too, where he works under the guidance of Professor Gonzalo Guillén Gonçalves, with a strong background in sustainable process systems engineering. He earns his PhD from the University of Alicante in Spain, focusing on the sustainability trade-offs in industrial CO₂ utilization for chemical synthesis. At ETH Zürich, Juan Diego, his research supports the development of net zero strategies for the chemical sector, with a particular emphasis on evaluating the economic and environmental viability of innovative synthesis pathways for fuels and chemicals. Juan Diego's research interest also extends to the green chemistry, sector coupling, and industrial symbiosis. So, Juan Diego, thank you very much for coming here today and for making this presentation in this event. The floor is yours. Thank you very much.
Thank you, Alejandro, for the very nice introduction. So, yeah, today I wanted to talk to you about decarbonizing the chemical industry and what effects and side effects this has. So, as you may know, nowadays the anthropogenic carbon emissions grow year after year, and most of these emissions come from the energy sector. But also the production of chemicals and fuels is quite relevant. And in order to meet the climate targets set by several organizations, we really need to tackle this sector. But in order to do this, we need to know how this works, right? So I will explain what is being done nowadays. So as you may know, also the chemical industry heavily relies on fossil carbon and energy, mainly coming from natural gas and also petroleum. And this, in addition to the environmental issues that this brings with it, it also has some availability issues that came into light recently with current geopolitical conflicts and the supply chain of natural gas in Europe. Now, the way this works is that we use these resources to synthesize a set of platform chemicals such as methanol, ethylene, or benzene that are the base of most of the more complex molecules that we can find everywhere. The alternative then is to use renewable carbon, for example, captured from the air or from biogenic resources, and renewable energy from wind, solar, or also biogenic sources, to alternatively synthesize these platform chemicals and then downstream decarbonize all the other chemicals. However, this approach, even if it seems like very straightforward, comes with several trade-offs. Not only economic, because the renewable energy is expensive, but also environmental. And for this, I will use the synthesis of fuels as an example. So nowadays, we go to our well, and then we extract our fossil oil, and then we go to our refinery, and then we purify, we get our gasoline, kerosene, and diesel. Now, if we wanted to decarbonize this process, instead of going to the well, we would need renewable energy to produce renewable hydrogen, green hydrogen from water splitting, and also we would need a renewable source of CO2, such as direct air capture, or DAC. Then we would go to a new facility in which we will use these raw materials to produce synthetic crude using the Fischer-Tropsch process. Then we would go to our regular refinery with, well, some modifications to produce the electrofuel version of these regular fuels, e-gasoline, e-kerosene, and e-diesel. However, this approach comes with some issues. First one is that getting this green hydrogen and capture CO2 requires higher energy demand. And the second one is that these processes are also usually low material efficient, since most of this hydrogen is then lost as water after the reaction in order to activate the CO2 molecule. Now, what happens here is that if we evaluate the carbon footprint of this new process, if we compare the fossil production of, in this case, diesel, with the synthesis using this Fischer-Tropsch process for e-diesel, we see that, yeah, depending on the electricity source, we may actually improve the carbon footprint, which was our main goal. But if we go further into other environmental indicators, such as human health or ecosystems quality, we see that if we compare the impact of the fossil version, we actually have collateral damage in these impact categories, a phenomenon known as burden shifting. And I'm not even going to go into the production cost, which is another problem, and it will increase at least by 3 times. So the problem here is that we are not only using the same process and adding additional steps to produce these raw materials, in addition to another process to produce the zinc crude. So what can we do now to decarbonize this properly, and so you don't have burden shifting? So, well, the idea would be to technically change the process completely. And I will use the example of the vinyl chloride monomer to illustrate this. So if you're not familiar with this chemical, the vinyl chloride monomer, or VCM, is the repetition unit of polyvinyl chloride, or mostly known as PVC. So essentially, to get our VCM, we need to react ethylene, which comes from petroleum, and also chlorine, which comes from an electrolysis process. This one is easier to decarbonize. And then we go through a chlorination step, which won't produce the vinyl chloride. It will produce an intermediate called EDC, the ethylene chloride, which, in addition to other byproducts, like 3-chloroethylene, which we need energy to separate. On top of that, we need to crack the EDC, which requires, again, more energy to produce a mixture of EDC and VCM that then we need to apply more energy to separate. But on top of that, we are producing hydrogen chloride as a byproduct that we really need to valorize in order for this process to be economically feasible. So we need more ethylene and also oxygen to go through another oxychlorination reaction, which will, again, enable all this separation sequence, because we also produce CO2 as a byproduct and other things. So, of course, if we were to decarbonize this process by changing the source of ethylene and chlorine, we will still need to deal with all this energy. But what if we change the source of the vinyl chloride, the main raw material? What if we use ethane instead? So the process potentially could become this simple by just changing the raw materials. And in a single step, we would be able to produce vinyl chloride with hydrogen chloride as a byproduct still. Now, we studied this process, and as you can see here, for the carbon footprint, if we compare the business-as-usual ethylene-based vinyl chloride process with the potential of this one-step synthesis from ethane, we see that there's a potential decrease in carbon footprint. But not only here, also we can see this in human health and ecosystems quality. And even more pronounced if we look into a prospective scenario in 2050 with the decarbonized electricity sources, where the advantage becomes even more evident. And here, but you may be asking, what happens with the cost, right? As we said that in the other example, the cost would triple. Well, here, if you see here, comparing the business as usual with our new process, and not even the ideal step, we would also see at other scenarios here, it is already economically feasible. So in this context is where the value of the Photo2Fuel project comes. You are already familiar with it, but our idea is to produce chemicals and fuels using CO2 and sunlight by combining microorganisms that have been evolving for millennia to very selectively produce a specific chemical with man-made artificial photosensitizers that excel at harnessing very efficiently the energy from sunlight. Together, they form semi-artificial biohybrid systems, in this case to produce acetic acid. So now let's get familiar how acetic acid is produced industrially. In this case, acetic acid is mainly produced via methanol carbonylation. So we need natural gas, and then we need a high-temperature process called reforming to produce syngas, which is a mixture of hydrogen, carbon monoxide, and and CO2. And then we need to tune this composition to produce methanol. On the other side, we need also more natural gas, to produce, again, more syngas, and then to separate the carbon monoxide using cryogenic distillation at very, very low temperatures, to finally go into the acetic acid process and synthesize it. Now, if we wanted to decarbonize this process, we would need instead to use renewable energy with water to produce green hydrogen, and then using captured carbon dioxide to produce green methanol. And for the carbon monoxide, we'll need, again, more hydrogen and more carbon dioxide, and use the reverse water-gas shift reaction, and also another separation process to produce the green carbon monoxide to finally go into green acetic acid. So as you may see, these are a lot of steps which require a lot of energy. Alternatively, we have our low TRL but very promising processes that in a single step, as a semi-artificial photosynthesis, by just using sunlight, water, and carbon dioxide, can produce acetic acid. But this is not the only process. We can also find others, like this gas-to-acid, or GTA, which just requires methane and carbon dioxide in a thermal process to produce acetic acid. Now, these processes are very easy to decarbonize, because in the first one, we only need a renewable source of carbon dioxide, and in the second one, we could just substitute the methane and the carbon dioxide with biogas, which already has the composition. What happens here is that if we compare the carbon footprint of all these scenarios, first you can see the business as usual and the carbonized variants. Then we have the GTA and the carbonized variants, and also the semi-artificial photosynthesis, is that if we compare the carbon footprint of the business as usual with the decarbonized business as usual, we win, which is something that we were seeing in other scenarios. But if we also look at the other one-step processes, we see that the performance may even surpass to the decarbonized bow. However, what happens if we go further into other impacts? Here you can see the performance in human health, ecosystems quality, and resource scarcity. And if we compare with the business as usual, we see that actually decarbonizing directly the business as usual doesn't produce any carbon footprint, any burden shifting, sorry, in neither of the scenarios, which is surprising given all the steps and all the energy required, but still feasible. But what happens with the cost? What is no surprise here is that if we compare the cost of the business as usual with the decarbonized business as usual using green hydrogen, the cost doubles, which is something that doesn't happen if we see the direct processes that synthesize acetic acid directly from CO2. So from this presentation, the only thing I wanted to for you to remember are two take-home messages. The first one is that decarbonizing chemicals and fuels usually comes with trade-offs, mainly economic, but also environmental. And we could actually skip these issues here by leveraging non-conventional synthesis routes that directly produce these chemicals by more efficient energy and material utilization. Thank you for your attention. This is what I wanted.